Hello, welcome to this lesson on volumes of solids by using cross sections. The method is also known as slicing. That's how you'll often see it referred to otherwise in textbooks. Think of it as having a loaf of bread, and you wanted to determine the volume of that loaf of bread. So one way you could do it is to slice it up and determine the volume of each individual slice, and then add together all those volumes. Very similar to what you did when you used rectangles underneath a curve to approximate the area under the curve. This is very similar to that. So allow me to take you to a website that's really good in terms of the visuals in showing you parallel cross sections. All right, so there's four, probably just these three we'll take a look at. So let's start with one. All right, so you can see it animated. It will run again. All right, and that's what the figure looks like in the end. All right, so notice how each of those cross sections are equilateral triangles. All right, so as you can tell, they kind of are smaller at the ends and they're larger, taller triangles in the center. So if you could imagine having infinitely many triangles like that and figuring out the volume really of each individual triangle, it will have a little bit of thickness to it, but not much. That's one way you can determine the volume of this three-dimensional figure. And take a look at the base as well. All right, notice in this case it's an ellipse. And as you take cross sections, in this case they're equilateral triangles, the shape of those cross sections really determine the shape of the entire three-dimensional figure. So let's take a look at another one. All right, now this is going to have the same elliptical base, but notice how now the cross sections are squares. And notice how the shape of the figure is different from the previous one. Again, the squares get taller in the middle. And remember with squares, the base and the height are the same. So at its widest, that's going to happen at the center of this ellipse. So that's one reason really why at the center that it's the highest, because that's also where the base is the longest. And then towards the ends, they get a little bit smaller. All right, so let's look at one more. Again, an elliptical base, but this time the cross sections are whole circles. This one basically looks like an egg or a football. Again, it's at the center of the ellipse that the circle is going to be its largest with the longest diameter, and they get smaller towards the ends. All right, so let's return to our lesson then. So there's a pretty simple way in which you can determine with calculus the volume of a three-dimensional figure if you want to determine that volume by using cross sections. The first thing you'll need to know is if your cross sections are going to be perpendicular to the x-axis or to the y-axis. All right, the top one is the x-axis. All right, you'll notice that if your cross section is perpendicular to the x-axis, it is a dx problem. Another thing to note is that your limits of integration, the a and b values, will be x values. Now, if your cross sections are going to be perpendicular to the y-axis, then it becomes a dy problem. And in this case, your limits of integration are y values. So each problem will come down to this. Now notice what you're taking the integral of. Notice how you're taking the integral of an area. So basically, we will have a plan of action as to how we do these. You'll notice that as we go through each of the problems, I'll provide for you as examples. So the first thing we'll do is find the length of the base. And you'll notice as we do the examples for you that I'll be coming up with a sketch of what the base will look like. Just like in those other ones, the base was an ellipse. Oftentimes the base is going to be created by two different curves. And we're going to find the length of that base. And we're going to use a representative rectangle, much like you would have done when you did area under a curve by using inscribed rectangles. And to get the length of that representative rectangle, think of it as top minus bottom. If it's going to be a cross-section that's perpendicular to the x-axis, a dx problem, or if it's a dy problem, because your cross-sections are perpendicular to the y-axis, you're going to go right minus left. And you'll come up with an expression for the area of the type of cross-section that you're told you have. Typically, they're going to be squares or equilateral triangles, semicircles, or rectangles. And for the rectangles, you'll typically be told what the height is. And then finally, you'll set up your integral to find the volume. All right, so here's the first practice problem that we'll do. You trying to find the volume of a solid whose base is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1. And the cross sections are going to be perpendicular to the x-axis. And in the first one, we want our cross sections to be squares. All right, so let's take a look at the graph of this. All right, you'll notice I have the two equations set up under y equals on my graph. Go ahead and graph them. All right, so we want the area that's bounded here in the center, kind of right here, this sort of oblong shape. So let me change the window a little bit so we can see it a little bit better. All right, so it's this part that goes, it looks like from -1 over here on the left over to probably 2. You would have to find those points of intersection because they're going to become your limits of integration. So let's go ahead and find one of those really quick just to be sure. It should be -1. Yes. All right, and this other one should be 2. All right, now since our cross sections are going perpendicular to the x-axis, we know this is a dx problem. So our limits of integration, they are the x values of these points of intersection. All right, so our limits of integration in this case are going to be -1 to 2. All right, so if we take a look at the sketch really quick of this. All right, so here's -1 over here. Here's 1 and here's 2 over here. They kind of intersected up here. Won't be the most perfect graph. All right, so here's the equation, x plus 1. The parabola, little lopsided. All right, so the area we're trying to find is this one in here. That's our base of this figure. So when we think of the representative rectangle, all right, remember it's perpendicular to the x-axis. All right, this is really the thickness of the squares that are your cross sections. So as we set up the integral, all right, remember the first thing we want to do is find the length of the base. All right, and it's top minus bottom. So on the top, that representative rectangle is hitting the curve x plus 1. On the bottom, it's hitting x squared minus 1. So if we simplify that, all right, so that's how long this base is of your square. All right, the next thing we want to do is find the area of that square, because that's the type of cross-section we have. All right, well, remember area of a square is, side squared. One side has length -x squared plus x plus 2, and we have to square that. So that represents the area of that cross-sectional square. So finally, to get the volume, you're simply doing the integral from -1 to 2. They were our limits of integration, remember, from the x values. It's always the area of whatever type of cross-section you're taking. And we knew it was a dx problem. So at this point in your calculus career, feel free to evaluate that in your calculator. And when you do so, feel free to pause this and double check. You should get 8.1 if you care to pause this and try it on your own. And that represents the volume of this shape that's created. And as we go through these problems, you'll notice we're doing the same steps every time. Pretty easy. So we're going to use the same diagram for our next one. We're just going to change up the type of cross section we have. All right, so we're next going to look at rectangles that have a height of 1. All right, so if we think about it, the base hasn't changed at all. All right, so your length of the base is still the same. Right? We just need to change the area of the type of cross section. So remember, it's a rectangle with height 1. Oh, this is equilateral triangles. I guess we'll do equilateral triangles first. I skipped the other one. We'll do equilateral triangles since we're here. All right, now you have to remember how to get area of an equilateral triangle. There is a formula for it that's really handy to know. I would highly suggest you have it committed to memory. The area of an equilateral triangle specifically, remember it's square root of 3 over 4 times the length of the base squared. Again, a very handy formula. No, they do not give it to you on the AP exam. So in this case, it would just simply be square root of 3 over 4 times that length of the base squared. So the volume of this figure, when the cross sections are equilateral triangles, we still have the integral from -1 to 2. And it's simply you're taking the integral of the area of that specific type of cross section. Again, feel free to evaluate that on your calculator. Pause if you wish. And you should come out with approximately 3.507. And we'll go back and do the rectangle one. All right, notice it's the same 3 steps every time. All right, so let's go back and do that rectangle one that we accidentally skipped. All right, the length of the base is still that negative x squared plus x plus 2. All right, so now we're doing area of a rectangle with has height 1. Well, area of a rectangle is simply the base times the height, so that's easy. So the volume, integral from -1 to 2 of that specific area. All right, feel free to pause to try that on your calculator. Oh, and actually I think it's exactly. So not approximately equal to, I do believe it comes out exactly correct, equal to it. It should be 4.5 that you get. So as you do several of these, you'll start seeing they're pretty much all the same. Same 3 simple steps to get your answer. All right, so I have one more for us to work through that we can try. All right, this time our base is going to be created by the curve y equals x cubed, y equals 0, so the x-axis, and then the vertical line x equals 1. And we want to find the volume of the solid, and this time our cross sections are perpendicular to the y-axis, so this is going to be a dy problem. Now because of that, remember, since it's a dy problem, your integrand needs to be in terms of y. All right, so you might have to be rearranging specifically that y equals x cubed equation. All right, so if you think about what this looks like, it's simply a cubic equation, so we know what that looks like. All right, so here would be our curve. All right, let's say x equals 1 is here. All right, so if it's bounded by the curve and the line x equals 1 and the x-axis, we're talking about this part right here being the base of your figure. All right, so if we think about our representative rectangle, but remember our cross sections are now perpendicular to the y-axis, they're going this way. All right, so as we go to find the length of our base, this time we're going to be doing right minus left. All right, so first type of cross section are squares. So let's find the length of the base first. All right, well, if we did right minus left, okay, on the right side, that representative rectangle is hitting 1. On the left, it's hitting x cubed. All right, but there's a problem because remember this has to be a dy problem, so we cannot use it as x cubed. So what we have to do is think, okay, we got to rewrite this equation really as y to the 1/3, the cube root of y is equal to x. So instead of doing it as x cubed, we're not going to use it this way. We're going to use it as 1 minus y to the 1/3. Right? Remember, there has to be consistency in your variables. If it's a dy problem, your integrand must be in terms of y. So as we set up our volume, we need the area for the square then. Right? Remember, that's just base times height. So if our base has length 1 minus y to the 1/3, our height has to be the same since it's a square. And you can simply leave it like that. You do not have to multiply it out. So when we go to get our volume, now remember this time our limits of integration have to be y values. So the y values are going to extend from 0 on the bottom. We would have to know this point of intersection up here. Right? That's the point 1, comma 1. Right? So it's the y value of 1, but they are y values. So we're taking the integral of the area that we had. All right, now as you do this in your calculator, you can just, substitute an x as you do the integration in your calculator. You don't have to use y's. You can put them as x's. Or, if you want to put them as y's, you can put them as y's too. It will give you the correct answer either way. All right, so if you want to give that a try, feel free to pause this. You should have it coming out as approximately 0.10. And we'll look at the same scenario with 2 more types of cross sections. All right, the next ones are going to be isosceles triangles of height 4. Now, the length of the base is still the same. All right, now if we're talking isosceles triangles of height 4, all right, remember area of a triangle, 1/2 base times height. All right, so the base is the 1 minus y to the 1/3. Height is 4. So that simplifies to 2 times 1 minus y to the 1/3. Then finally, to get the volume, limits of integration remain as 0 to 1, the y values of that specific area. And this one for you should be coming out approximately 0.5. Not so bad. So we have one more. All right, let's consider if our cross sections this time were semicircles. All right, length of base remains the same. Now we need area of a semicircle. So remember that's going to be 1/2 pi r squared. All right, so 1/2 pi. Now, remember this 1 minus y to the 1/3, that's the entire base. The radius is going to be half of that. All right, so the radius we obtain by taking half the length of the whole base. All right, but then we have to square that whole thing. All right, so when you simplify it, remember the denominator 2 gets squared, so that's a 4 times the 2, that's the denominator out in the front, so you have pi over 8. So that becomes the integrand for our integral in the volume. So this one should be coming out approximately 0.039. And that's how you find volumes of three-dimensional figures by using cross sections.